Welcome to this explainer. Today, we're setting the stage to unravel a truly profound, centuries-old physics mystery about the fundamental nature of reality itself. We are going to explore something called action emergence, and specifically the Extremal theorem. You see, for a long time, classical physics has carried this strange, almost magical assumption right at its core. But recent work in discrete mechanics and computational frameworks, well, it's completely flipping the script on how we understand the laws of the universe. So, let's dive right in. Here is the big question. Why does nature always seem to choose the path of least action? Think about a ball thrown through the air, or a ray of light bending as it enters a pool of water. They don't just take random, chaotic paths. They take the exact mathematical trajectory that minimizes a quantity called action. But wait. How on earth does a particle seemingly know the optimal path from its starting point to its finish line before it even begins to move? I mean, does the universe have some grand top-down calculator constantly checking all possible futures? For centuries, physics has answered this question using Hamilton's principle, which you'll often see written mathematically as delta S equals 0. It states that the physical trajectory of a system is the one that extremizes the action. But here is the catch. Classical physics treats this action-minimizing behavior basically like magic. It's viewed as a fundamental, top-down rule imposed on the universe from the outside. Nature just obeys it and, well, end of story. But honestly, that answer is starting to look pretty incomplete.
Let's look at the massive contrast here. On one hand, we have the classical view, nature minimizes action as an external postulate. It's basically a command from above. But on the other hand, we have a radical new perspective from the Nexus framework, which says that action emergence is a compiled consequence of local consistency. So what does that actually mean? It means the universe isn't looking ahead to minimize some global path. Instead, macroscopic physics, those grand sweeping curves of planets and light, is actually a compiled artifact. It's a global pattern generated entirely from tiny, discrete, local rules checking for consistency at every single step.
That brings us to Section 1. The Change Axiom Chain and the foundation of reality. To truly grasp how this works, we have to zoom way in to the absolute smallest scale of reality. The entire framework starts from a surprisingly simple active computational field. Step 1 is C0. Distinction exists. Because without distinction, there's just a frozen, unmeasurable void. But distinction alone isn't quite enough, which brings us to Step 2, C1. Distinction must continue. This is the absolute mandate of change. Nothing is allowed to just freeze. Because distinction exists and must continue, Step 3 kicks in. A constraint is formed to map out how that continuation can legally happen. And finally, Step 4, a local transition occurs. So really, the universe is built on distinction combined with mandatory continuation, which forces these constrained local transitions.
Now, we hit a genuinely crucial rule in this system. Transformation must pay a price to prove something changed. This introduces the core concept of cost. Think about it. If a transition had zero cost, it would be perfectly undetectable, which is a direct violation of our very first rule that distinction must exist. Every single local transition has to pay a price to prove a change actually happened. And it's exactly this cost landscape that prevents the universe from exploding into unconstrained chaos or freezing into total stasis. It forces a perfect, dynamic balance.
Moving right along to Section 2, the ledger of change and compiling the path cost.
So we have these tiny local transitions paying a tiny local cost. How does that actually translate to the continuous world we see around us? Well, we can draw a direct bridge between these discrete computational concepts and continuous classical physics. For instance, that local transition cost in our logic chain, that is exactly what physicists call the Lagrangian. It's simply the cost of a field configuration changing over a tiny step of time and volume. And if you look at the accumulated path cost, the total bill for all those tiny steps combined, that is exactly the action, denoted as S. Finally, the strict requirement that every step is locally admissible, that translates perfectly to Hamilton's principle, delta S equals 0. Let's break down how this builds mathematically, because it's super elegant. You start by simply summing up the local transition cost over discrete steps, literally adding up the toll at every single node. Then, as you apply the continuum limit, making those time steps approach 0, that discrete path cost directly converges into the action functional. That's the famous integral of the Lagrangian over time. The massive takeaway here is that the action isn't some abstract mathematical ghost assumed to exist beforehand. It is quite literally just the accumulated price of local transitions.
Which brings us to the climax of this explainer in Section 3, the Extremal theorem.
First, we need to clearly define local consistency. The framework calls this C1 consistency. It means a field configuration where every single local transition is an admissible continuation of its neighbors under the compiled constraints. In plain English, every single node in the active field must lawfully continue. It absolutely cannot violate conservation, and it cannot violate locality. It has to agree perfectly with its immediate neighbors.
And here is the step-by-step bidirectional equivalence chain that proves the whole thing. Think of it like a chain reaction. If a field is C1 consistent everywhere, that mathematically translates to the compiled wave equation equaling 0 everywhere. Step 2. If the wave equation holds everywhere, that means the Euler-Lagrange equations hold. And finally, standard variational calculus tells us that if the Euler-Lagrange equations hold, then delta S equals 0. They are mathematically identical. Hamilton's principle isn't some separate mystical rule. It is the exact mathematical equivalent of every local node simply playing by the rules of its immediate neighbors.
So we arrive at this major paradigm shift. The physical trajectory is the path where local constraints globally agree. Delta S equals 0 isn't a magical global calculation. Nature isn't looking from the start line way out to the finish line to find the cheapest route. Nature is just looking at the very next step, making sure it legally balances with its neighbors. When every local step pays exactly what the compiled rules require, no more, no less, the resulting macroscopic path is naturally the extremal path.
Let's wrap things up with Section 4, a compiled reality. To summarize this entire shift in how we view physics, let's look at one final contrast. Hamilton's principle is not an external rule placed on trajectories from the outside. That's the old way of thinking. The new way is seeing it as a compiled consequence. It is simply what locally admissible continuation looks like when viewed from above. The universe is endlessly, relentlessly executing local instructions, and the grand, beautiful, continuous laws we've discovered over the centuries are just the compiled output of those tiny, rigid local constraints.
I want to share this profound quote from Dean Kulik that brings this whole compilation metaphor to its ultimate conclusion. He says, "A program is a shaped space in which certain futures become natural. Matter is a computation whose cost landscape has stabilized." Just think about that for a second. Matter itself isn't just inert stuff sitting in space. It is an active computation, a process that has found a stable rhythm in the universe's transition cost landscape, continuously replacing lost distinctions with new ones.
Which leaves us with a truly stunning final thought. If Hamilton's principle is actually a compiled output, and if matter itself is just a computation stabilizing its cost landscape, what else in our reality is waiting to be decompiled? What other grand laws of physics are secretly just the macroscopic shadows of tiny local logical constraints? Thank you so much for joining me on this explainer, and I really hope this leaves you eager to dive deeper into the true computational nature of our universe.